we are going to figure out how to calculate the actual mechanical advantage and the ideal mechanical advantage. Remember those from the last video. But this time we're going to do it for an inclined plane. Inclined plane, which is really just a fancy word for a ramp. So we can put a ramp here. I'll call it a ramp for now because it's easier to write that and talk about it. All right. An inclined plane is a different kind of simple machine. And we've already talked about the wheel and axle and gears and pulleys and the lever. So let's talk about the inclined plane today. This will be a short one and not too difficult, I don't think. So let's draw a picture of a ramp. Now what does a ramp do? Well, a ramp is for lifting. So even though we're moving sort of sideways as we slide up the ramp, really what we're talking about is we're talking about lifting. And of course the height of the ramp, which would be this distance over here, that's called the height of the ramp. That's how high you're going to lift something. If you slide something from the bottom of the ramp to the top, then this would be how high you've moved it, right? So the height of the ramp. The other thing we have to think about is the length of the ramp, which is how far you have to go up the ramp. So we'll call that length of the ramp. Now, because a ramp is actually lifting, the picture might look a little funny when we draw it. Let me show you what I mean. I'm going to draw a picture here of a block that we're going to push up the ramp. And if we push up the ramp, we would have to push here with an applied force. And I'm going to give us a number. Let's just say that that applied force is 80 newtons. 80 newtons that we're going to use. That's how much effort we have to make to slide this block. Now, what we're actually sliding against is the weight of the block. The weight is the load force. When you lift something, the weight of something is a load. But there's a little bit of a difference though. When you lift an object straight up and down without a ramp, then the downward load force is the weight, right, of the object that you're lifting. And the weight, remember, is mg. It's the force of gravity. And then the effort force you make is the lifting force up. And if you want to lift something, you have to have an effort force that is equal to the weight, and then it'll lift. But this is a little bit different because we're not lifting straight up. We're sliding up the ramp. However, the effort that we are working against is still the weight of the object. So I'm going to draw my effort force here. I'll draw it in purple. My effort force is, my load force. The applied force is the effort force in blue up there. So the load is here. This is the load force. And it's equal to the gravity, the weight, mg. But we're not going to worry about that. I'm going to tell you. Okay, that's what it would be. But I'm going to tell you what the load force is, because calculating it out is a little bit more complicated than we want to get into. So let's just say that the load force is 150 newtons. And it's taking us 80 newtons to slide it up the ramp. Okay? So obviously the ramp is making our life easy for us. The other thing I might do here is, instead of saying F applied, why don't I just call this the effort force, because that's what we've been calling it, right? This is the U pushing or pulling. So that's the effort force, and this is the load force. And then you might say, well, how come then the effort force is not pulling against the load directly? It looks like it's on a weird angle. And again, that's because of the ramp. But you still are fighting the weight of this object. Now, the other thing that you're fighting against, I'll put it in for a second, but we don't really need it because I've already worked it into the question. The reason why you might need extra force is you have friction on the ramp. Force of friction. And the force of friction, which is pulling against you, is something that would take away from your effort force, wouldn't it? It would require you to use a larger effort force than you might have needed. So with a ramp, what we try to do is we try to reduce the friction as much as possible. We want to make our ramp slippery. We could grease the ramp, or we could put the block on wheels. Wheels have much less friction than if you're sliding something. We could do all kinds of things. So that's the reason why the ramp might not be perfect. Okay? Without friction, whoops, I need my marker here. And we'll use black. Let me just write something down here. Without friction, if you could get the friction to be completely zero, the ramp would be ideal. And ideal means, if you're an ideal ramp, it means that your IMA, your ideal mechanical advantage, is the same as your actual mechanical advantage. But in real life, that hardly ever happens because of the friction. The friction makes this change. It makes the actual mechanical advantage actually a little bit less than the ideal mechanical advantage. And we're going to learn how to figure out both. So let's start with the actual mechanical advantage. We'll have to move down. Actual mechanical advantage is exactly the same as it was for every other simple machine. So that's the good thing. You don't have to learn anything new. It is equal to, and we just have to remember which one goes on top. For AMA, it's the load force divided by the effort force. So in my case, if I look at my picture that I've drawn, okay, the load force is 150 and the effort is 80. So this would be 150 divided by 80 newtons. And of course, if you do that, it'll be not quite 2, right? Because 150 divided by 80 is about 1.88. Right? So what that basically means is every newton that I push up the ramp with can lift 1.88 newtons. That's why it's an advantage. It allows me to lift 1.88 newtons with only 1 newton of force. And don't forget, the reason I can do that is because I'm going to push it a longer distance. And speaking of distance, let's go back to our picture. Let's put some numbers for the height of the ramp. Let's say our ramp is 4 meters high. And let's say that the ramp length is 8 meters long. Those are the numbers that I set it up with. So now, in order for you to get the IMA, the ideal mechanical advantage, it doesn't depend on the forces because it's just basically depends on the structure of the ramp. So for the IMA, for a ramp or inclined plane, you don't use the forces. What you do is you take the length of the ramp. That's kind of like, if you think about, remember the other IMAs were calculated with for the lever, for instance, it was the arm, right? And it was the effort arm divided by the load arm. Remember that? R for the load. And they all had to do with R's, which were distances. Well, for the ramp, those load arms is not really an arm, it's not a lever. But the lengths of the side of the ramp, the length of the ramp, right here, is considered to be the effort arm, because that's the distance that you are pushing your object up the ramp. It's the distance that you're pushing your effort over. So the length of the ramp, okay, that's kind of like the effort distance. And then divided by the height of the ramp, which is what actually happens to the load, right? Height of ramp. That's like the load distance. It's how high you manage to get your load to go. So that's kind of like the load distance. So it is kind of the same thing, right? It's the effort arm length over the load arm length, but it just doesn't look like arm lengths with this. So we write it like this. So for my particular picture, I had an effort length of 8. And so the IMA would be 8, and the height of my ramp was 4, and it should come out to 2. So the ideal mechanical advantage is 2. So what that means is that every Newton I use pushing up the ramp can lift 2 Newtons of weight. So the ramp is giving me double my money, isn't it? It should, anyway. But because I have a little bit of friction on my ramp, I worked in a little friction when I put those forces in there, you can see that the actual advantage isn't quite double. You don't get 2 Newtons for every pushing Newton of effort. You only get 1.88. So 1 of my Newtons of effort can lift only 1.88. But even with the friction, it's still better, isn't it? Because if you were just lifting straight up, then 1 Newton of effort can only lift 1 Newton of weight. So this ramp is giving me extra force, it seems, to make me able to lift or push larger, more massive objects with bigger weight. But there is a trade-off. Notice how the distance that I have traveled up the ramp is 8. It's much longer than if I had lifted it up. So you can lift with big force over small distance, or use an inclined plane, and you can push with smaller force over bigger distance and get the same amount of work done, or at least get the same job done. And even if you do a little extra work against the friction, you can see that you're still getting a pretty good advantage. You can never get the ideal. You're never going to get 2, because that's only in a perfect world without friction, right? But you can get pretty darn close to it. And if I were to make the friction even less, I could get this number maybe even closer to 2. Maybe I could get 1.97 if I put lots of grease on the wheels and I put a little dolly underneath. There's lots of ways of getting the friction reduced. So that's how you do an inclined plane, IMA and AMA. And why don't I just give you, as part of this video, I'll give you a couple of questions that you can try just to practice. But I won't make an assignment about this. So this is just for you to try. You don't have to hand this in. Let's just take a couple of ramps, and let's say that we have 10 meters up the ramp like this, and we'll make this 7 meters up. The height of the ramp is 7, right? So you have to calculate the IMA. What would the IMA be? And it's pretty simple, right? You just have to put the right numbers in the right place. And then if I told you about forces, let's put ourselves, I'll use a different color for the forces so you can see that differently. Let's put this here, and let's put our effort force pushing up the ramp this way. And let's have the load force, which is the weight of the object. And I'll tell you what those are. Okay? And I'm going to have to pause for just a moment while I figure it out, because I have to figure out with the friction so it comes out to a realistic number. So 1 second. All right, so what I'm going to put here is effort force of 50 newtons. And we'll make a load force of 68 newtons. So you can see how your effort is a little bit less. If you wanted to lift this, you'd have to apply 68 newtons of force to lift it straight up. But with the ramp, you can get away with 50 newtons. Okay? So then you have to figure out what the AMA is. All right? So now what you do is pause the video, see if you can figure those two out if you haven't already. And when you're done, come back and we'll just do it together and make sure you understand what you're doing. So take a minute, pause the video, figure them out. And I'm assuming now you're back and you figured them out and you did the IMA. I'll just write them in up here. I'll take my question marks away. The IMA would be the length, 10, divided by the height, 7, which I think comes out to about 1.43. But the AMA would be the load force, 68, divided by the effort force, which is 50. And if you divide those Let me see, 68 divided by 50 should come out to about 1.36. Not quite as good as the ideal. So you lost a little bit because of friction, right? The friction means that the reality or the actual mechanical advantage that you can get is only this. But it's still pretty good because look, this is what it would have cost you to lift it. To lift it straight up, you have to match the weight. But we can get away with 50 newtons because our ramp is a simple machine that lets us use smaller force with a bigger distance to lift a larger force through a smaller distance. And that's the end of that. And I think that's pretty much the end of this Unit 2. And so what you'll see very soon is a Unit 2 unit test that you'll have to complete once you've finished your assignments. And you can submit that in the Dropbox, and I'll get that up as soon as I can.